Hey guys, let's look at the properties of rational functions. So rational functions are quotients of polynomial functions, okay? And this just means that rational functions can be expressed as f of x equals p of x divided by q of x, right? Where p and q are polynomial functions and q cannot be 0 because, as we know, we can never have a 0 in the denominator. The domain of a rational function is the set of all real numbers except the x value that makes the denominator 0. So let's find the domain of each of these rational functions. So when we are looking for the domain of a rational function, we always, let's just write this here. This is a rational, right? And that implies that we're going to set the denominator not equal to 0 and solve. Oh, not equal to 0, sorry. And solve. So we just take whatever's in the denominator. This time it's x minus 3. We set that not equal to 0 and solve, which means that we're going to move the man. This stands alone. So x cannot equal 3. We're going to put it on a number line. Some of you may not have to do this, just for some of you who do need to. So we can have any number, right? We always assume all real numbers, but we cannot have it be 3. So here's our 3 on the number line. So it could be any number here, but it absolutely cannot be 3. So our domain is going to equal negative infinity to 3. Remember, when we make this jump, we denote it with the union, and then 3 to positive infinity. And that would be our, our domain. Okay, let's do another one. Again, it's rational, so we're going to set the denominator equal to 0 and solve, right? I'm not going to write it over again. Same instructions. So we're going to have x squared minus 9 cannot equal 0. Move the 9. So x squared equals 9. Now we have to get rid of that square root. The square, sorry. Gosh, I answered the wrong question. How do you get rid of a square with the square root? Dadgummit. I hate when I do that. So the square and the square root cancel, leaving us with x equals plus minus 3. Please don't ever say square root of 3, because we've already done that operation to get the 3, right? Again, let's put it on our number line. But this time, we have a negative 3 and a positive 3. It could be anywhere here, here, or here, right? So our domain will equal negative infinity to negative 3. Again, we have to jump negative 3, picking back up on the other side, going to 3, make another jump, so we denote it with the union, pick back up on the other side of 3, and go on to positive infinity. And this is our domain. Okay, let's do this last one. And you're probably thinking, golly, Michelle, this one looks a lot like the other one. Well, it does, right? But this is the difference of two squares, and this is the sum of two squares. So we still take it and set it equal, not equal to 0. And then we move the 9 over. So it's going to leave us x squared cannot equal a negative 9. Again, same trick, right? To get rid of the square, we take a square root. But we can see that now we have problems, right? Because we have a negative underneath an even root. So we know what that's going to do, right? That's going to throw us into the imaginary realm. So this is going to be x equals plus minus 3i. Let's talk about this for a minute. Jump over here, where? Down here, how about that? So if we have like a negative underneath here, that's the same thing as saying -1 times 9, okay? So I'm just going to talk about the -1 portion. So if you have the square root of -1, that always equals I, right? Pull him out as an imaginary. Now, a little tip for your homework. If we were to square both sides, I'm going to do that down here. So if I take the square root of -1 and I square that, well, we know that a square and a square root cancel, right? So if I cancel those and I also square this I, we're going to get -1 equals I squared. So this may be a little fact that you might need for your homework at some time. So I'm just going to leave it right there for you guys, okay? But this is an imaginary number. Sorry, lost my train of thought. It's an imaginary number. So imaginary numbers never affect real numbers, right? And that's what we're talking about here. We're talking about real numbers when we talk about domains. So imaginary numbers do not affect our domain. So our domain here is going to be -infinity to +infinity, right? Because our domain for a polynomial is all real numbers. Important word, real numbers. So the real zeros of the denominator q of x, although not in the domain, play an important role in the graph of a rational function. And we're just going to scroll up and find out what that is, okay? That is, they become the vertical asymptote of rational functions, the VA, if you will. So vertical asymptotes of rational functions. So the definition of a vertical asymptote. The line x equals a is a vertical asymptote of the graph of a function f if f of x increases or decreases without bound as x approaches a. Excuse me. So you can see here, I'm going to use this color. Here we have our f, and as it approaches a, here's a, it's going to increase without bounds, right? It goes off to infinity. So as x approaches a from the right-hand side, because it's coming from the right? And then it goes, f of x approaches infinity. Okay? Same thing here. As f approaches a from the left-hand side, then f of x approaches infinity. Same thing here, right? It's coming toward a from the right-hand side, and f of x approaches -infinity. Just made our thing mess up. And then as x approaches a from the left-hand side, that's what this little symbol up here at the top, this means the left-hand side, this means right-hand side. Sorry, I should have said that over there. So as x approaches a from the left-hand side, f of x goes to -infinity. So, thus, as x approaches... Ooh, that's not my highlighter. Sorry. As x approaches a from either the left or the right, f of x goes to infinity, or f of x goes to -infinity. That is what an asymptote is, okay? It's an imaginary line on your graph that it's an imaginary line on the Cartesian plane that your graph will not cross. There, that's what I'm trying to say. Having a little bit of difficulty getting it out. There you go. If the graph of a rational function has a vertical asymptote, they can be located by using the following theorem. So here's our theorem. If f of x equals p of x over q of x, if it is a simplified rational function and a is a real zero of q of x, the denominator, then the line x equals a is a vertical asymptote of the graph of x. So to determine a vertical asymptote of a simplified rational function, this is very important, it always has to be simplified, okay? Set the denominator equal to 0 and solve. Since a vertical asymptote is a vertical line, It must be expressed as an equation of the form x equals a number. I want you to go even further than that, because x equals a number can just be a line. I want you to write it like VA, or you could do a capital A, I don't care, at x equals whatever number it is, okay? But if you do not put VA at to let me know that it is a vertical asymptote, I will count off points on your exam. A rational function may have several vertical asymptotes, okay? So there can be more than one vertical asymptote on a graph. The graph of a rational function will never intersect the VA. So the graph will not cross your vertical asymptote ever. It's impossible. When graphing a rational function, the vertical asymptote is denoted by a dashed line. So asymptotes are always denoted by dashed lines, okay? Very important. Ooh, that's not what I wanted. And it never intersects, so never cross. And you can have several of these, okay? Alright, so let's do a couple. Okay, we're going to find the VAs, if any, and graph them on the Cartesian plane. Okay, so the first one is x over x squared minus 9. So we know that the VA is always from the denominator, right? So we're going to set the denominator equal to 0 and solve. That's our instructions. So x squared minus 9 equals 0. Now we're just going to solve. So we move the 9 over. Alright. Now we got to get rid of the square root. I said that again. Get rid of the square. Good grief, Shelley. So the square and the square root cancel each other. So x equals plus minus 3. Okay. So we're going to say VA at x equals negative 3 and 3. Always listed as two numbers. I do believe that's how your homework wants it as well. So then at negative 3, we're going to put our little dashed line. Ooh, that's a terrible dash right there. And then a positive 3. Okay. Okay, now let's consider B. We have x plus 3 over x squared minus 9. And remember, we always have to be sure that they are simplified, okay? So let's write this in a factored form. So this is going to be x plus 3 over x plus 3, x minus 3, right? Because this is the difference of squares. So we know that one's going to be plus and one's going to be minus. So when we write it this way, it's very easy to see that we can cancel our x plus 3's, leaving us with 1 over x minus 3. Now let's stop and talk about this, because when we have cancellation, when there's cancellation, there's always, there's either. There's always a hole at x equals a. Okay, so at the factor that we canceled. Sorry, that was hard for me to say. At the factor we canceled, there's always a hole at x equals a. So we're going to take the one that we canceled. So that's going to be x plus 3. We have to set that equal to 0 and solve to see where our hole is going to be. So I'm going to write hole here. So we just subtract 3 from both sides. So we know our hole is going to be at negative 3. So we're going to plug our negative 3 back in here to see where our the ordered pair where our whole exists. So we take 1 over negative 3 minus 3. That's going to give us 1 over a negative 9. 6, sorry. Good Lord, 6. So that equals a negative 1/6. So our ordered pair is going to be, our x was a negative 3. It's a different color so we can see it. So negative 3, negative 1/6. Okay, so that's where our whole is going to be. Alright, so now we can go ahead finding our vertical asymptote. I'm going to jump back to green. So we know that we're going to take the denominator, set that equal to 0, and solve. So now we have our x minus 3, set that equal to 0, add 3 to both sides, so x is going to equal 3. We're going to put VA at in front of it so we know that it's our vertical asymptote. And now we can go ahead and put at 3, our vertical asymptote. And then at negative 3 and negative 1/6, ooh, that's going to be super small. Let's go a little bit. Negative 3, why are they doing that? Negative 1/6 is going to be our other one, okay? It's going to be our, ooh, it's a hole, Shelly, it's a hole. So we have to make it an open circle because that's how we denote a hole. And I need to put that over here with the rest of our notes on hole. I'm just going to put denoted. Denoted by an open circle. So if we were to pull up our, goodness, if I can find our calculator. So alpha equals enter, we'll have x plus 3, and then go down, and then it's going to be x squared minus 9. And we can graph that. And then we can see here is where our hole is. And then this goes off like that. So at negative 3 is where our hole is. Let's see if we can zoom in some more. Ooh, too much. Man. It doesn't really show it very well, does it? That's our hole. And then we can just go ahead and draw a graph. So there we go. Our asymptote. So n is less than m, so that's going to give it at 0. So come in. And this one looking like this. Alright, let's look at C. This one's a little different. It looks a lot alike, but they are different. So this is the difference, the sum of squares. Sorry, not the last one was the difference of squares. This one is the sum of squares. So how they differ is we're going to have x plus 3 on top. Since it's a plus sign, we know that it's going to be, we're going to have 2 parentheses, and they're both going to have an x. I guess I should write this better. But they both get plus minus, but this gets a 3i, and this gets a 3i. Okay, they're imaginary. And we can prove this by going about it a different way. I'll show you. So we can take x squared plus 9 and set him equal to 0. That's another way to do it. So if we subtract 9 from both sides, then we'll have x squared equals a negative 9, right? We know that we get rid of a square with the square root, same way over here, to reach a plus minus. But we can't have a negative underneath, right? So we have to pull out our I. So these cancel, leaving us with x equals plus minus 3i. Then when you move this back over, that's where we get our plus and minus from here. So there's the proof of where I get that. And now we know that well, we already know this, but x-intercepts are always real numbers, right? And we know that this guy is imaginary. So since he's imaginary and these are always real, we're going to have the denominator has no real zeros. And this implies no vertical asymptotes. Okay, so there will be no VAs. Okay, so this is multiplicity and vertical asymptotes. Remember in 3.1 that I mentioned odd degree polynomials have opposite behavior at the end, and even degree polynomials have the same behavior at the end. Let's look at this. The multiplicities of real zeros in the denominator can be used in a similar fashion to determine the behavior of a graph around each vertical asymptote. So if it has an odd multiplicity, we can see that x is going toward 2 from the left, then x is going to negative infinity. And if x is going to 2 from the right, then x approaches infinity. Now with odd multiplicity, if x approaches 2 from the left, then R2 of x approaches infinity. Or if x approaches 2 from the right, then x approaches negative infinity. So you can see, like, if it approaches 2 from the left, it goes off to infinity, right? But if it approaches 2 from the right, it goes to negative infinity. That's all it's saying, is if your graph comes from the left-hand side, it's going to shoot off to infinity. Or if it comes from the right-hand side, it's going to shoot off to infinity, right? But if you have even multiplicity, and x approaches 2, like here's 2, and approaches 2 from the left, then it's going to go to positive infinity. That's when it has even multiplicity, right? The arrows go up, they go the same way. And if x approaches 2 from the right, then it's going to go off to positive infinity. Same thing, even multiplicity here. If it approaches 2 from the left, it's going to go to negative infinity. And if it approaches 2 from the right, it's going to go negative infinity. So if it's odd multiplicity, they're going to go in different directions every time. If it's even multiplicity, they're going to go in the same direction every time. Okay? So here's the conclusion. If the multiplicity of the real zeros that give the rise to the vertical asymptote is odd, the graph approaches positive infinity on one side of the vertical asymptote, and it approaches negative infinity on the other. That's if it's odd. If the multiplicity of the real zero that gives rise to the vertical asymptote is even, then the graph approaches either positive or negative on both sides. Okay. I'm going to stop here and we'll pick back up with horizontal asymptotes on the next video.